Hello friends, welcome to my channel Physics with Rakshit. In the present lecture, I will explain two solutions of black hole information paradox in loop quantum gravity, that is Planck star and remnant scenario. This preprint is archived in preprint platform. Those who are interested to read in depth can find it and download it to read it. In this preprint or paper, Planck star and remnant scenario, that is solution of black hole information paradox in loop quantum gravity, are elaborated. Since black hole is the final fate of collapse scenario or gravitational collapse, firstly gravitational collapse with two possible final outcomes, that is black hole and naked singularity, is outlined. Thereafter, black hole thermodynamics, along with four laws of black hole thermodynamics, Hawking radiation, brief introduction to information theory, and cause of information paradox are explained. Thereafter, solution of black hole information paradox outside the loop quantum gravity are briefly explained. LQG can solve information paradox by its natural cutoff on the value of quantum volume operator, that is 10 raised to minus 105 meter cube. In LQG, a star, namely Planck star, is also proposed, which is formed at Planck density and resides at so-called singularity point. Since LQG removes singularity through big bounds and proposes Planck star, which provides enough room for information to escape, so it can solve information paradox. LQG also predict remnant of black hole of the order of 10 raised to minus 14 meter, which is under current technological regime. In the remnant scenario, black hole makes quantum transition into white hole, and this white hole behaves as a long-lived remnant that can solve information paradox. So I will start with the introduction of gravitational collapse. Let us see what is gravitational collapse. In the study of gravitational collapse, it involves study of singularity that is introduced at the last phase in case of stellar collapse. Study of coordinate singularity, which is resided at r is equal to 2m or event horizon, and curvature singularity, it means r is equal to 0, which is resided at the center of black hole, has raised many questions in physics. Coordinate singularity is actually the boundary of black hole, namely event horizon, whose actual singularity resides at r is equal to 0. Because of strong gravitational pull of black hole, even light cannot go beyond event horizon once it is trapped inside this boundary. So this is how much powerful gravitational pull of black hole is. Thus, event horizon prevents outside observer to communicate with inside observer or vice versa. At the singularity of black hole, general relativity fails since it couldn't remove infinity that is introduced through singularity. These failures suggest that one needs quantum theory of gravity that can successfully explain singularity introduced in stellar collapse or gravitational collapse and at the time of Big Bang. After the discovery that the entropy of black hole is related to its area but not its volume by Bekenstein, Hawking suggested that black hole also emits radiation, namely Hawking radiation. It means after some times, because of the radiation, black hole will be evaporated completely. So what will happen to information that is resided inside the black hole? That this question creates information paradox. Here I have explained in this paragraph, it means black hole is not totally black. Hawking successfully derived the formula of black hole entropy, that is Bekenstein-Hawking entropy formula. Hawking suggested that due to Hawking radiation, black hole will eventually evaporate and the information of interior of black hole is lost for forever. But information is always conserved according to principle of unitarity of quantum mechanics. This principle is the integral part of quantum physics. So this raises a paradox, that is black hole information paradox. Therefore, either considered physical phenomena is wrong that involves violation of this principle, or one doesn't know the theory through which information can be recovered. There are many possible solutions of black hole information paradox given by various theories such as anti-de Sitter conformal field theory, correspondence complementarity, AMPS firewall, fuzz wall, soft hair, quantum halo, baby universe, etc. I have just stated all this solution which is outside of low quantum gravity. In this lecture, I will explain two solutions of black hole information paradox that belongs to low quantum gravity, that is Planck star and remnant scenario. So first of all, let us see what will be the final outcome of gravitational collapse, whether it is black hole or naked singularity. General relativity proposes that final fate of the collapse of a massive star is either black hole or naked singularity. In case of naked singularity, curvature regions formed during the gravitational collapse and ultra-high density are visible from far away observer, and there can be observational consequences. So one can have observational quantum gravity effects. In case of gravitational collapse of massive stars, quantum gravity is needed to understand the resulting space-time singularities. In case of such collapse, what happens? Event horizon is created gradually. If any star enters into this horizon before it reaches to the final stage of collapse, a singularity, that is, then a black hole is created. If the event horizon doesn't form or delayed with gravitational collapse, then a naked singularity is created. Big Bang is one of the such singularity that was occurred 13.7 billion years ago and visible to far away observer by observations. Another kind of naked singularity is that occurs in case of gravitational collapse of massive stars. Those who are familiar with the diagrams of general relativity and gravitational collapse can easily see that in case of naked singularity, because of outgoing null geodesics, one can say that information can easily gone out, while in case of black hole, because of the presence of event horizon, information cannot be easily gone out. It is internal condition that determines whether the final outcome of gravitational collapse is naked singularity or black hole. So here it is internal conditions, that is parameter in terms of initial data within the star, such as velocity of collapsing shells, density, pressure, which may be tangential or radial, that determines whether singularity is hidden or visible. In case of realistic assumptions, naked singularity also do occur in gravitational collapse. For example, gradual decrement of density from center to outer layers of collapsing forms naked singularity at the final collapse stage. Earlier, I have explained Schwarzschild metric, which is the basis of black hole physics and which is one of the solution of Einstein's field equation, in which space-time was assumed to be spherically symmetric, exhibiting a point mass at the center of symmetry but totally empty, and the geometry that is far away from source was assumed flat. According to this spherical vacuum symmetric solution, black hole is created. And here I have given the equation of Schwarzschild metric. I have also explained this in my one of lecture of my YouTube channel. Viewers can find that description. That equation given by Schwarzschild has mathematical anomalies. So after Schwarzschild, Eddington and Finkelstein came up with their coordinate, which is crucial to make Schwarzschild metric non-singular at r is equal to 2m. Schwarzschild metric predicts that at coordinate singularity, it means at r is equal to 2m, metric becomes singular, which is not true. So this issue was resolved by Eddington-Finkelstein coordinate, which is given as ds square is equal to in bracket 1 minus 2m over r into dv square minus 2 dv dr minus r square in bracket d theta square plus sin square theta d phi square. Here in this coordinate, while approaching to r is equal to 2m, light cones don't become very narrow and light cones tilt over that region. You can see in this image when light cone approaches to coordinate singularity, that is r is equal to 2m, they tilt towards event horizon and don't become very narrow as explained in Schwarzschild metric. And in this coordinate, since time and radial coordinate reverse their character inside coordinate singularity, this issue is resolved. So in this diagram, one can see involved tilting of light cone after r is equal to 2m. Thereafter, in the 1960s, Kruskal and Zicre developed another coordinate system by considering global approach of general relativity, which could separate coordinate singularity with actual curvature singularity. Coordinate singularity occurs at r is equal to 2m, while actual singularity occurs at r is equal to 0. So this difference was explained by Kruskal and Zicre in 1960s, and their metric is ds square is equal to 32 meter cube over r into e raised to minus r over 2m into in bracket du square minus dv square plus r square into d theta square plus sin square theta d phi square. Here u and v behaves as global radial markers and global time markers. In this diagram, I have shown Kruskal metric with 4 different regions. Those who are aware with this diagram of light cone can easily understand these 4 regions. Similar to Schwarzschild metric, another important theory that explains black hole physics is OST model, which was given by Oppenheimer, Sider, Dutt in 1930. They studied continual gravitational collapse of a pressureless dust, homogeneous density distribution with uniform density matter cloud. The formation of event horizon in collapse was proposed in OST model, and it is the salient feature of this model. Event horizon is created before the creation of singularity in case of black hole. Hence, one who resides outside the event horizon cannot communicate with inside observer. Since event horizon behaves as cutoff surface for outside observer, so Schwarzschild geometry is in the integral part of OST collapse. This model is proved to be crucial in the understanding of active galactic nuclei, quasars, and radio galaxy. A star which is homogeneous made of spherical dust with no pressure is converted into black hole at the last stage of collapse. In realistic condition, most of the stars are not fully spherical. These stars are inhomogeneous and also possess rotation, and thus during collapse their shapes are distorted and their rotational speed also increases. So in 1969, Roger Penrose conjectured that an event horizon does always form in case of final stage of collapse under reasonable physical conditions. Such a conjecture is known as cosmic censorship conjecture. This conjecture is the base of black hole physics. One of the famous solutions of Einstein's field equation is Kerr-metric, that is rotating axisymmetric solution. According to one of the conjecture of no-hair theorem, end state of collapse is Kerr black hole, which has mass as well as spin. Kerr black hole drags their adjacent spacetime in the direction of rotation. So Penrose suggested that such effect permits a rotating black hole as a source of energy. Because of rotation, this black hole leaks energy out for outside observer. Here in this table, discrepancies between black hole and naked singularity are briefly summarized, and it is necessary to understand remnant scenario and Planck star. Naked singularity is crucial in loop quantum gravity to provide solution of black hole information paradox. Earlier in my YouTube channel, I explained this discrepancy. So within a shorter time, I will explain this discrepancy to save time. First discrepancy is in case of black hole, singularity is censored by event horizon, while in case of naked singularity, singularity is visible. Information or object that fall inside the black hole cannot be observed by far away external observer because of event horizon, while in case of naked singularity, it is possible. Black hole holds cosmic censorship conjecture, while naked singularity violates this conjecture. Black hole is created in case of homogeneity, uniform density distribution, symmetrical, pressureless, spherical, stellar, or galactic collapse, while naked singularity is created in case of inhomogeneity, non-uniform density distribution, non-symmetrical, non-spherical, stellar, or galactic collapse with non-zero pressure, shear of spacetime, and in case of black hole that rotating or having charge. In black hole, event horizon created before singularity creation, and hence it is known as black hole, while in naked singularity event horizon is delayed. Let us see some basics of laws of black hole thermodynamics. Similar to thermodynamical laws, here one can study laws of black hole thermodynamics. In 1973, Bardeen et al. Gave 4 laws of black hole thermodynamics for axisymmetric solution of Einstein's field equation, in which stationary state of rotating black hole is axisymmetric. In this equation, area of event horizon capital A and surface gravity K is analogous to entropy and temperature of thermodynamics respectively. So let us see zeroth law in black hole thermodynamics. Surface gravity K is constant over the event horizon for a stationary black hole. This law is analogous to zeroth law of thermodynamics. Let us see first law. Here K over 8 pi is analogous to temperature. This law is analogous to first law of thermodynamics, that is delta U is equal to Q minus W. The relation between two neighboring stationary axisymmetric solutions exhibiting a perfect fluid with circular flow and a central black hole is given as delta M is equal to K over 8 pi delta A plus omega BH delta JBH plus integration omega delta dj plus integration bar mu delta dn plus bar theta delta ds. Here m is mass of black hole, Omega BH is angular velocity of black hole, JBH is angular momentum of black hole, delta DJ is the change in angular momentum of the fluid, delta DN is the change in the number of particles, delta DS is the change in the entropy, and bar mu is the red shifted chemical potential. Bar theta is the red shifted temperature. Let us see second law of black hole thermodynamics. This law is analogous to second law of thermodynamics, that is, entropy either increases or remains constant, delta S greater than or equal to 0. For any black hole, area of black hole never decreases with time. So delta A greater than or equal to 0. Third law tells that it is impossible to reduce surface gravity k is equal to 0 by any procedure by finite sequence of operations, whether it is idealized. This law is analogous to third law of thermodynamics, that is, at absolute zero temperature, the entropy of system becomes constant. If one throws particle into a black hole to increase its angular momentum and to decrease its surface gravity, then the decrement in the value of surface gravity k occur per particle thrown in. So it gets smaller and smaller as the ratio of angular momentum to mass approaches to 1, that is j over m square is equal to 1, and at last it becomes 0. For j over m square tends to 1, idealistic accretion process also exists, in which an infinite divisibility of the matter and infinite time are required with the addition of finite rest mass. There is a possibility of naked singularity in case of k is equal to 0. Infinite number of operations by reducing k to 0 creates naked singularity. Through this process, an asymptotic predictability is violated that is necessarily for black hole physics. So, naked singularity is the practical solution of gravitational collapse, while various solution of Einstein field equation tells that black hole is always created. Let us see Bekenstein-Hawking entropy formula and Hawking radiation, which is the cause of information loss in case of black hole information paradox. In 1971, Bekenstein found that entropy of black hole is proportional to its area but not its volume. In the equatorial form, it is written as S is equal to alpha A, where alpha is universal constant. Later on, Hawking found that black hole also emits radiation and it is not completely black. Previously, it was believed that black hole doesn't emit any kind of radiation and it is completely black. But Hawking came up with one mathematical formula which tells that black hole also emits radiation. That radiation is Hawking radiation and it has also temperature. It means temperature is inversely proportional to mass of black hole. If we remove proportionality, we will have equation TBH is equal to h cut c cube over k 8 pi g mbh. Black hole's temperature is proportional to its inversely proportional to the mass of black hole. In case of classical physics, black hole can only absorb but cannot emit radiation. To explain emitting black hole, Hawking suggested that if quantum mechanical effect is considered, it causes creation and emission of particle, that is virtual pairs of particles from black hole. It seems as if black hole is emitting radiation and it also has temperature. Due to continuous thermal emission, the mass of black hole gradually decreases, and which is the cause of information loss in the end. In case of black hole, it means that one of the particle of virtual pair that is created due to relativistic quantum mechanical effect near event horizon of black hole goes in and another particle comes out. So ingoing particle brought negative energy flux with it into black hole, an outgoing particle takes away positive energy flux outside the event horizon. So, ingoing particles that possess negative energy flux cause this event horizon of black hole to shrink towards the singularity, and eventually this black hole will be disappeared. By considering Bekenstein's conjecture, Hawking also gave the equation of entropy of black hole, that is Bekenstein-Hawking entropy formula. SBH is equal to K beta A over 4 LP square is equal to K beta C cube over 4 GH cut. A is equal to alpha A, where alpha is universal constant, is equal to K beta C cube over 4 GH cut. So in this diagram, I have shown how black hole evaporates in the end because of virtual pair of particle. Black hole with few virtual pairs of particles near event horizon from infinite pairs in space-time and one pair in which ingoing particle and outgoing particle is shown here. So here among several virtual pairs of particle I have just shown one pair of particle as a demonstration. Let us see brief introduction to information theory. In 1990, Wheeler proposed that information is the basics of the physics of the universe. Wheeler used the phrase that it from bit, it means whole universe comes from these bits. In quantum information theory, information of the state of a quantum system is defined by quantum information, and qubits are basic units of quantum information. Quantum information is the fundamental physical entity of study in quantum information theory. Quantum information processing techniques is used to manipulate quantum information. It is defined in terms of von Neumann entropy that I will explain soon. Information is deeply related to entropy in physics. Hence, for any thermodynamical system, entropy is written as S is equal to minus K beta summation J Pj ln Pj, where Pj is probability of happening. Boltzmann equation of entropy that is valid in the microcanonical ensemble at thermodynamic equilibrium is S is equal to K beta ln omega. It means number of microstates corresponding to macrostates. In information theory, information I is a measure of missed or incomplete information. Claude Shannon proposed that the entropy S of a system in terms of information cannot be lower than the entropy of any its constituent parts. Shannon gave generalized equation of information that is I is equal to minus C summation J is equal to 1 to capital U Pj ln Pj, that is analogous to Boltzmann's equation. John von Neumann found that in quantum mechanics, the quantum state can also be represented by another mathematical object, that is density matrix instead of wave function. This density matrix is written as rho is equal to summation j pj ket vector psi j bre vector psi j. The density matrix explains a statistical ensemble of different quantum states. It is also used to represent pure or mixed quantum states. In case of pure state, the considered quantum system exhibits zero entropy, but in practical, it is impossible. The value of probability of any quantum state is unity, then one can have complete knowledge of that quantum state. That is practically impossible. So there is always incompleteness, and ensemble can have different quantum states. So ensemble is a mixture of quantum states. In case of one pure state, there will be one non-zero eigenvalue in density matrix since probability is unity. If state is mixed, then the density matrix has more than one non-zero eigenvalue. If the eigenvalues psi j implies that the probability is that the quantum system is in state j, then the density matrix is diagonalized. The eigenvalues of density matrix is equal or greater than 0 and it is Hermitian. Those who are interested in these concepts can read my preprint, that is solution of black hole information paradox in loop quantum gravity. I have explained all these terms in that preprint. The trace of density matrix is 1. In this case, here von Neumann entropy can be written as S is equal to minus trace rho ln rho is equal to minus summation j rho j ln pj. So this is the basic of information theory which is required to understand various solution of information paradox in loop quantum gravity. Let us see how and why information paradox occurs. The main cause of information paradox is Hawking radiation. If we consider classical mechanics, there will be no evaporation, hence information will not be destroyed. As according to classical mechanics, black hole cannot emit any kind of radiation. However, one cannot reach to this information because of enormous gravitational pull of black hole. In case of earlier, I have explained that at the center of black hole, warping of space-time is too intense to reach at that point. In case of quantum physical treatment, black hole will be evaporated after several years due to Hawking radiation and information is completely lost for forever, which is not possible according to quantum mechanics principle of unitarity. Since the area of black hole is proportional to entropy and entropy can be understood in terms of information, one can increase the area of black hole by throwing a single or more bits of information into black hole. It means the black hole information paradox can be understood by considering pure state matter that form a black hole after collapse. After complete evaporation, black hole leaves Hawking radiation, which is thermal in nature. Therefore, initial pure quantum state is now converted into a mixed state. A transition from pure to mixed quantum state is not unitary, and that is why information lost occurs, as it violates basic principle of quantum mechanics, that is principle of unitarity. Earlier, I have given various solution of black hole information paradox outside loop quantum gravity. There are mainly two solutions of black hole information paradox in loop quantum gravity, that is Planck star and Remnant scenario. There is a no sharp boundary between Planck star and Remnant scenario as a solution of black hole information paradox in loop quantum gravity. First of all, I will explain what is Planck star. In loop quantum cosmology, when energy density is near to Planckian, the quantum gravitational pressure counterbalance gravitational pull and remove singularity through reversing the gravitational collapse. In my YouTube channel, I have explained this scenario in one of my short. Due to this reverse collapse, a black hole is bounced. The Planck star is resided at this point where energy density is of the order of Planckian. This whole process is shorter in local proper time but takes several years for the outside observer because of time dilation of huge magnitude. So bouncing cosmology is the result of pressure produced by quantum gravity effect that prevent gravitational collapse. Since effect of gravity is controlled by Planckian density, volume of bounce is bigger than Planckian. So the resulting object is bigger than Planckian by a factor in bracket m over mp raised to n, where mp is the Planck mass and m is the initial mass and n is positive. Previously, it was believed that quantum gravity manifests itself at Planck length, but actually quantum gravity effect manifests itself when energy density becomes of the order of Planckian. So Planck star resides at universal singularity point when collapsing matter reaches to that point. So Big Bounce model explain eternal cycle of expansion and collapsing matter. So here in this diagram I have shown quantum transition through Planck star from black hole to white hole. In loop quantum cosmology, collapsing object bounces into white hole or towards expanding region. Since quantum gravity effect is considered and Heisenberg's uncertainty principle plays important role to avoid singularity. It produces repulsive gravitational force that stops collapsing body to reach at singularity and hence singularity is disappeared. Thus the volume of bouncing universe at matter dominating phase is V is equal to m over mp Lp cube. Here m is the universe total mass. Quantum gravity effects starts to appear at this volume to Planck volume. So this is the case of universal collapse. Let us see what happens in stellar collapse. When extra energy falls into this star, it condenses the core of collapsing star and it becomes heavily compressed core whose density is of the order of Planck density. Thus, such collapsing star is converted into Planck star for a while in its local proper time. Since quantum pressure balances the attraction of gravity, here time becomes slower near massive object according to general relativity and for considered volume, mass of Planck star is very big. The size of Planck star is R is approximately equal to in bracket m over mp raised to n into Lp. Here m is the collapsing star's mass and n is positive number. If the value of n is taken here, then the resulting Planck star's size is 10 raised to minus 10 centimeter, which is quite small compared to actual star. Therefore, Planck star is very denser star or a bouncing phase through which collapsing star avoids singularity and converted into another phase, that is white hole. One can one can understand the bending of light cones near inner and outer horizon. In case of Planck star, in loop quantum cosmology, light cone tilts inwards near outer horizon, that is r is equal to 2m, and become narrower between inner and outer horizon, that is in between r is equal to r and r is equal to 2m. Because of density gradient, in this case star exhibit two horizons, that is inner and outer horizon, and becomes normal when it enters into Planck region. In this diagram, I have shown how light cone bends toward inner horizon and tilts toward inner horizon from outer to inner horizon using Eddington-Finkelstein coordinate without considering evaporation scenario. The curvature R is related to Planckian density, that is rho p. In bracket, R is approximately equal to 8 pi rho p. By taking order n is equal to 1 by 3 in the equation, R is approximately equal to m over mp raised to n Lp. One gets R in approximately equal to m over mp raised to 1 by 3 Lp. Similarly, the surface area of Planck star will be A is approximately equal to in bracket m over mp raised to 1 by 3 Lp square. Till this moment, I haven't considered evaporation of black hole. Now, By considering black hole evaporation through Hawking radiation, simultaneously outer horizon is contracted slowly and inner horizon obtains positive energy. So a particle having negative energy falls in and becomes a particle with positive energy, and expansion of inner horizon takes place. Due to Hawking radiation, outer horizon is contracted until it comes to the expanding inner horizon. Thereafter, there is a no horizon. It means black hole has no longer event horizon and it is now naked singularity with no horizon. At this place, entrapped information can be obtained. Since information can easily escape from this place, this occurs when energy is of the order of Planckian, but not at the value of Planck length. So this is the point which should be noted by viewers to understand the mechanism inside the Planck star. As mentioned, such an object is not long-lived, but remnant of this object is long-lived. Enormously large, which is enormously large, whose order is bigger than Planck length. So here in figure, I have shown how Planck star forms and what happens at that time. The quantum gravity effects through shaded area where general relativity doesn't work, that I have shown in this figure. The dark dashed line shows trapping horizon in which the outer is evaporating or contracting and the inner is expanding. The dotted line shows outer or external boundary of collapsing star. The point Pi and Pf are initial and final point of boundary of external horizon. The arrows are Hawking radiation. I'm talking about the second image, and there is an absence of event horizon at the lowest light line where Hawking radiation is absent. In the left side of image tells about Planck star in Eddington-Finkelstein coordinate with evaporation, while I have described second image which shows Penrose diagram of Planck star. In the second case, where value of n is 1, it means that value of R in is approximately equal to in bracket m over mp/lp. It is known that near event horizon of black hole, the tidal gravitational force is too strong, hence equivalence principle of general relativity is violated. For the second case of study, consider that quantum field states is similar to the vacuum near horizon, where the second law of black hole thermodynamics roughly holds. However, the equivalence principle is not violated near horizon, and there is no firewall that incinerates the infalling observer. If you are aware about what happens when any observer falls inside the event horizon, you might be aware about this scenario. Each one of the particle of Hawking pair that goes out is entangled with the infalling one maximally that goes on to Planck star. So information in the Planck star cleanses the Hawking radiation entropy. This internal entropy follows law of Bekenstein bound. With the expansion of inner horizon, its entropy increases, while the entropy of outer horizon decreases with contraction. When the inner horizon comes to outer horizon, the information that is resided in a star is ought to at least equal to the escaped information through Hawking radiation. So a black hole that considers quantum gravity acts differently since the inner core of such a black hole can memorize the original mass. And as per estimation, the one-third mass of total mass is emitted out in the evaporation process. At the end of evaporation, there is absence of horizon in this scenario of Planck star. Hence, information that is resided inside the black hole can escape easily due to pressure of quantum gravity. Here, Planck star may provide experimental signature to detect quantum gravity effect, especially blue quantum gravity, by the study of a spectrum of different masses that are generated in the early era of universe by primordial black holes. One can predict lifetime of such primordial black hole. For instance, the lifetime of a primordial black hole whose mass is of the order of 10 raised to 12 kilogram is 14 into 10 raised to 9 years. That means such a black hole is at the end phase of its age, as its age is approximately equal to the age of our universe, and by the age of universe one can decide the current mass of such a black hole. If energy is suddenly emitted from such a black hole due to effect of quantum gravity, it may be detected. The size of black hole with this mass is R is approximately equal to GH cut over 348 pi c square into TBH. So R is equal to LP square C over 348 pi into TBH. And final equation is R is equal to cube root of TBH over 348 pi TP into LP, which is approximately equal to 10 raised to minus 14. And here TBH is lifetime of black hole. TP is equal to LP over C is the Planck time, and R is obtained by a number that is achieved by the ratio of cosmological scale TBH to a Planck scale. This ratio is important for observation point of view. Energy range of this wavelength is of the order of mega electron volt to giga electron volt, which is detectable by current detector or current technology. However, this is yet to be detected. Let us see how Planck star-like object resolve issue of black hole information paradox. If we consider the size of final evaporation of black hole is of the order of Planckian, one cannot recover all amount of information that is trapped inside the black hole. In case of Planck star, this is not a big issue. Why? The size of black hole at final evaporation is bigger than Planckian size. So the information that is stored inside can be easily recovered. Hence, phenomena of bounce occur at Planckian density, but not at Planck length. Simultaneous occurrence of contraction of outer horizon and expansion of inner horizon establish the situation of naked singularity in which trapped information is released. The trapped information cleanses Hawking radiation, so there is absence of mixed state and pure state can be retrieved. So information is not lost, and no paradoxes occurred in the Planck star study of the quantum gravity. Second scenario that can resolve issue of black hole information paradox is remnant scenario. Here, the complete life cycle of black hole, that is quantum transition of black hole to white hole, plays important role in case of information paradox. And in the conventional quantum field theory, a black hole is disappeared after complete evaporation. But in loop quantum gravity, it tunnels into white hole that is vanished slowly after a long interval by emitting inside mass and trapped information. For macroscopic black holes, the probability of tunneling is little. However, that increases with mass decrement when such a black hole is near to the end of evaporation. At the end of evaporation, the black hole makes transition into a white hole which is long-lived and exhibit finite but large interior. Such white hole also exhibits horizon with Planck size. So the contraction of the area of horizon of the black hole due to Hawking radiation and interior tube's length increases with time and radius of tube decreases. Hence, A macroscopic black hole having M's zero initial mass after gravitational collapse exhibits little mass as well as surface area of horizon. So, black hole exhibits trapping horizon while the white hole exhibits anti-trapping horizon. Both are necessary to comprehend the complete cycle of black hole. The black hole of mass m0 exhibits long tube in its interior. After black hole makes quantum transition or bounce to white hole, the length of tube gradually with longer time period decreases during the evolution. Therefore, white hole is also known as long-lived remnant. In this diagram, I have shown that black hole's inner geometry exhibits finite long thin tube. Along with the time, the radius of this tube decreases with length increment. The classical black hole is shown in conformal diagram in the second image. Second image is a type of conformal diagram in which effect of quantum gravity is manifested at region P and Q. The lifetime of the black hole is given as eta bs is equal to b minus b0, where b0 is the advanced time of the collapse, b minus is the beginning time of the quantum transition. From figure, b minus is the advanced time of end of the quantum transition. Similar to black hole, one can have the white hole lifetime, that is eta wh is equal to a0 minus a plus. In this diagram, I have shown quantum transition from black hole to white hole with inside geometry depiction. This is kind of Penrose diagram where I have shown quantum transition from black hole to white hole. So how remnant scenario of loop quantum gravity resolve the issue of black hole information paradox? Let us see. Here, in case of this scenario, black hole information paradox can be solved using such white hole, since it behaves as long-lived remnant. In LQG, black hole makes quantum transition into a white hole. When such a black hole is near to the end of evaporation, these white holes having small masses and large finite interiors decay slowly through unitary process and can provide concrete solution to black hole information paradox. It means that the hole exhibits big capacity for storage of information. So remnant is long-lived and trapped information is slowly leaked from horizons and entropy is liberated. So a particle that went into interior of horizon can escape and cleanse the quantum state of exterior 1. This whole process doesn't violate the law of entropy bound, and that is urged by unitarity and consideration of energy. So here in this table, I have shown discrepancy between Planck star and remnant scenario. First point is the Planck star is an object that is created when the energy density of the collapsing star reaches to Planck density, so the information can have enough room to escape. The remnant scenario is a theory in which the black hole makes quantum transition to white hole and this white hole behaves as long-lived remnant and hence the information is conserved. In the Planck star theory, simultaneous occurrence of contraction of outer horizon and expansion of inner horizon establish the situation of naked singularity in which trapped information is released, while white hole behaves as long-lived remnant and it possesses small masses and large finite interiors that decay slowly through unitary process. Hence, the information is released. Theory of Planck star emphasizes more on size of the black hole at the time of final evaporation, that is of the order of Planckian density. This feature provides enough room to escape the information. While the theory of remnant scenario emphasizes more on the quantum transition of the black holes to the white hole in which the white hole is long-lived. The information is stored in the long thin tube of this hole, which provides enough room for the information to escape. So these are the conclusion of this lecture. There are four conclusions that I have explained. This is the preprint. One can find this preprint in the preprint platform. I have also given link and DOI number of that preprint. Thanks for listening and watching. If you like my video, please share and subscribe my YouTube channel. If you have any question regarding solution of black hole information paradox and associated concept, you can ask in the comment section. Thank you very much.